Okay, so this is the screen recording for the test corrections for exam number 1. I only have 5 minutes, so I'm just gonna get right into it. Okay, so question 1, I messed up part A and part C a little bit, and then part D I got it completely wrong. I just did part B as well, again, just because I wanted to do every part. So part A is the extensive quantities depend on the size of the system, while intensive parameters do not. I got that part right, but then I was a little confused, and my confusion was, far gone. I learned this really well through chapters 4 and 5, but that U, S, and V, energy, entropy, and volume, and also the number of moles, are extensive parameters, while T, V, and mu are intensive parameters, because they're, like I said, they're made of the ratios of the partial derivatives of du with respect to the extensive quantities like U or S or something like, or V. So that's the real answer for that, so I was just a little confused. And then this I got right. So then this was just asking what is du essentially equal to, and I just basically skipped the last term, but that du is equal to the quasi-static work and the quasi-static heat, and it also asks which are perfect and imperfect, and the answer is that u is actually the or exact and imperfect, and that these two are the imperfect quantities. And D asks, okay, which is not a fundamental equation, and it gives you these three equations, 1, 2, and 3, and I was like, oh, I'll just try scaling them with lambda. So I did that, and then I got it wrong because I didn't think that this first one here scaled with lambda, but indeed I see now that it does because I've got a lot more practice with that. And then this one does as well. You have, what is this, lambda cubed, I guess, over lambda times lambda is just lambda squared. Yeah, then the cubed over lambda squared is just lambda. So that works out. But this one, it does not. Lambda equals lambda squared, which we know is not true. So it defies the laws of thermodynamics. Okay, then we have question 1. Oh, right, this is the one that I made up. So I'm not really going to explain this because I just kind of made up the question. Define quasi-static heat work. What makes a product quasi-static? Then I define that right on the first 3 postulates in your own words, so I just kind of redefine them in the way I wanted to define them, which is the right way, just in my own words. This one was referring to question 4, and I just wanted to come up with a question that had to do with the same thing. Define with words and their representative equations what the fundamental equations of state are. Explain why the equations of state are homogeneous 0 order, and that's just basically saying why you can scale them with lambda and stating what they are and defining them and what have you. Okay, so question 2 I got a relatively correct, so I'm skipping that and going straight to question 3. So question 3 essentially asks in part A to take, we know that this 1 over t value is equal to 5u over n, and p over t value is equal to 5, are those the two things that were given? 5u over n, I guess. And then, so we know that ds du, which is essentially the same thing, is equal to 5u molar, and then ds dv, the same thing as this, is equal to 5v molar, which is just the exact same thing except the n taken out, which is what molar, basically what that little m does. So then you can take these two values, now that you know that, and kind of combine them to find the entropy, the molar entropy, which I think what we do over here. So yeah, I was like, okay, so the entropy molar is just equal to, this is some expression where, okay, you have to be able to take the derivative with respect to like u molar and then get this. So like if you have the derivative of entropy, the molar entropy, you say, oh, let's take the derivative of Sm with respect to u molar. Then this little 2 pops down right here, and then you get 10 over 2 u molar, and everything else goes away, which is 5 u molar, which is exactly what this is, which is actually a really cool thing. So you get that, and then you can convert back just to m, or excuse me, back to s by adding in that factor of 1 over n again. So then you get that as your final thing. Then you can check by saying, okay, so what's ds du, essentially 1 over t, ds dv, and ds dn, and you get these 5 things, or these 3 things, excuse me, and then you can plug them all back in and see that, oh, indeed, you get the right thing. And then for B, remember B was just like make up your own thing and see if it works, and that's what I did. And it was pretty simple because it was just S is equal to NV over U. And then for the one that I made up, it was very similar to, well, the second part of the one that I made up was extremely similar to the previous thing that I made up, but because, you know, it should just be a different form of the same type of question. So then this other one that I made up is that U is equal to 2nt, PV is equal to 3nt, and then 1 over T, solve, and then get this equation for dA molar. And then when you integrate, then you go down and you eventually finally get to this equation at the end here. Yeah. Okay, so question 4. Question 4 was regarding the if you have like some set gas and you're expanding it at constant pressure, and we know that for the first part of question 4, T final is equal to T naught, so it's at the same temperature, so delta U is equal to 0, and then we know, I actually got the first part of this right, that work is equal to negative nRT ln 5, or just, because in this case n was 1, so it's just negative RT ln 5. But I said mistakenly, oh, because T final is equal to T naught, there's no change in temperature, so Q is going to be 0. But obviously that's not true. We know that because of conservation of energy, delta U is equal to Q plus W, and therefore if delta U is 0, then Q is equal to negative W, or heat is equal to negative work, in other words. So that Q is just going to be the negative whatever work is. So it's this. It's the positive of the work. Yeah. So that was a little mistake that I made, but that makes absolute sense now. And then for B, we want to know what work and heat would be in the situation of pressure being constant and an adiabatic situation. And we know that work is still the same, negative V naught to V PdV, which ends up being negative 4 RT naught. And then we know, because of these equations, that the temperature final is going to equal this whole hullabaloo, but that a lot of things cancel, so then it just ends up being 5 times T naught. And then we know that du is equal to CNR dt, or change in T, so that delta U is equal to CNR T final minus T naught. We know that 5 T naught minus T naught is equal to, oh wait, what should that be? 5 T naught minus T naught is equal to, that should be 4. Well, that, yeah, should be 4 T naught. Anyway, it should be 4. So delta U is equal to 4 R C T naught, which is equal to 6 R T naught. So then that, once we have this, then we can kind of go back over here and plug in, oh, delta U is equal to the heat plus the work. Okay, so if Q is equal to, well, you just solve for Q, so then delta U is 6 R T naught, and work is negative 4 R T naught, which we know because we calculated from up here, then Q has to be 10 R T naught. So, and that's the end of the question. Oh, 10 RT naught is the end. Okay. And then we know work is negative 4 RT naught. And again, this should be a 4 there. So sorry about that. Yeah, and R is just Reinberg's constant in all these cases. It's just a constant number. So then lastly, the question that I made up for number 4 was pretty similar, but I just kind of changed the numbers around and made it different because I wanted it to be similar to the one that to the kind of problem that we did. 2 moles of a monatomic ideal gas are initially at temperature T naught and expand from V naught to 9 V naught. Calculate the work of expansion, and the heat absorbed if expansion is performed at constant temperature. So, kind of a similar idea where temperature final is equal to temperature initial, so delta U is equal to 0, and work is equal to negative integral PdV. And we know that you can just pull out the nRT because that's going to be constant, but then there's that 1 over V that you're integrating with respect to V, so okay, that's going to be a log from 9 V naught to ln V naught. So so it says right here actually, the ending of what you get from the integral is just nRT, because that's just a constant, times ln 9 V naught minus ln V naught. So then you know that work is equal to negative nRT ln 9, and Q, which is just going to be the positive, it's the negative, but it's the negative negative, so it's the positive of nRT ln 9. And because you're using 2 moles of the monatomic ideal gas, then work is going to be negative 2 RT ln 9, and Q is going to be 2 RT ln 9. Okay, I think that's the last thing. Okay, so, okay.